Okay, so let's look at some common cutting tools for the milling machine. First, we have end mills. They're typically made out of high-speed steel. They can come coated with titanium nitride. The more cutting edges you have, the higher the feed rate that can be used. But RPMs are still going to be the same, whether you have 2 flutes or you have 10 flutes. Here we have some carbide face mills. The carbide face mills use indexable carbides. The carbide has a higher cutting speed than high-speed steel. Carbide is harder than high-speed steel. Therefore, it's difficult to maintain a razor-sharp edge. Carbide requires pressure to cut. This is the reason why that a heavy cut will give you a better surface finish than a light cut. Here is a fly cutter. The fly cutter can use either carbide or high-speed steel. It's easy to sharpen, and you can adjust the size of the fly cutter. You sharpen it pretty much like you would a lathe tool bit. Cutting speeds are much faster, and you can multiply your cutting speed times 120%. Roughing end mills, such as these shown, are often called corn cobs, the one on the left, or crest cut, the one on the right. The purpose of these is to break up chips. They require less horsepower. There's less chatter, and they typically don't squeal when you come into corners. This is a shell mill. The shell mill is good for face milling and periphery milling. They usually come fairly wide so you can span a large expanse of a part. You need a very rigid setup in order to use this, and they require a bit more horsepower. Then we have specialty cutters, such as this radius cutter and ball mill. Here is a dovetail cutter and a woodruff cutter. And lastly, this is a slotting saw, but it's not the end of cutters that can be used in a milling machine. There's many others out there. Okay, before we start this project, one of the first things we want to do is prepare the mill by tramming the head and aligning the mill vise. Before we mount the mill vise on the table, we want to take a stone and make sure that there's no high spots on the table. Merely take the stone and just rub it over top of the table so that there's no burrs or anything on it. The same with the bottom of the vise. We want to just make sure that we just take the stone and just rub it across the bottom. If you feel a high spot on it, spend a little extra time to machine that or stone that off. We don't want to take too much off. Just want to take off any high spots or burrs that were caused by bolts or chips that were left underneath the vise. At this point in time, we have already trammed the mill in, and we have bolted the vise down to the table. Now I want you to notice that anytime we bolt this down, we should have washers up underneath the nut. Also make sure that the surface that washer contacts is free and clear of chips. Anytime that you come in and do work on the mill, you should double check the mill for tram. We can check the tram right here on the top of the vise and indicate the back of the vise. Now if it's out of tram, you want to take the vise back off the table and go and tram it in directly to the table, because that's always going to be your best bet. Tram on this part should be less than 1/1000th of an inch. Run out on the vise should be less than 1/1000th of an inch. Okay, so let's talk about what we're going to be doing. We're going to start off with a block of material that's 2 inches thick. It's going to finish up at 1 inch 375. So we need to consider that. So we're going to be taking 4 cuts across this part. First cut is going to be a roughing cut. Now, for a roughing cut, we're going to run 80% of the speed. And we're going to be using the 3-flute carbide mill. Carbide has a cutting speed of 400. From this, we need to figure out the RPM. Now, RPM is equal to the cutting speed times 4 divided by the diameter of the cutter. So in this case, the cutting speed is equal to 400 times 4 divided by 2 inches, the diameter of the cutter, which equals 800. Now, we're going to multiply that by 80%. And we're going to take that 800 and multiply that by 0.8. And that's going to give us 640 RPM. So 640 RPM. And then from this, we need to figure out what our feed rate should be. So, in order to do the feed rate, we need to know what the chip load is going to be. And that's designated by CL. It's a roughing cut. Now, our chart says that we can go up as high as 15 thousandths per tooth, but the fact is we don't have enough horsepower to really do that. So a good roughing speed for this would be a chip load of 0.005. From this, we can figure out the feed rate. Now, feed is equal to the RPM, and that's the actual RPM of the machine, not just our theoretical, which we figured out. The actual may be because we're using a machine that has belt drives. So it's RPM times the chip load times the number of teeth. So if our RPM is 640 times 3, times 0.005, 0.005 times the number of teeth, 3, that gives us 9.6 inches per minute. So our feed is going to be 9.6 Now, 9.6 inches per minute means we're turning this candle fairly fast. But how do we know exactly where we are? Well, we need to be able to break it down into a smaller segment. So let's take that 9.6 and turn it into seconds. So it's 9.6 inches in a minute. So if we take the 9.6 and divide it by 60, that's going to give us 0.16 inches per second. Now, from this, we can pretty much guess what this is. But if we take the turn of a handle, which is 200 thousandths, and divide it by that 1.16, we end up with 1.25 seconds. So that means that our handle is going to be turning 1 1,000, 2 1,000, 3 1,000. It's going to be turning a little slower than 1 second for a complete turn. So our feed per 200 thousandths is going to be 1.25.
Oh, our depth of cut here is something else we need to consider, depth of cut. And our depth on this case is going to be 80 thousandths. Because we really only have an eighth of an inch to work with. Our second cut is going to be a finishing cut. And we're going to run this at 100%. We're going to use this same 3-flute carbide end mill. Cutting speed is going to be 400. I want you to figure out the RPM. Our chip load is directly proportional to our surface finish. So if we're looking for a good surface finish, our chip load should be about 0.00, between 2 and 3 thousandths. So we'll give a chip load of 2 thousandths. You need to figure out the feed. You need to figure out the feed per 200 thousandths. And the depth of cut in this area, we should make this 0.005. Now, what I hope to accomplish from this is, I hope that you can see the difference in the surface finishes between these two cuts. Our third cut is going to be another finishing cut. And we're going to run this at 120%. And the reason we're running it at 120% is because we're going to do this with the fly cutter. We're going to use the high-speed tool bit on this. The cutting speed is going to be 100. Our chip load, again, is going to be 0.002. And our depth of cut should also be 0.005. Now, again, you need to figure out the RPM, the feed per 2,000. And then lastly, we're going to use that 4-flute end mill. Again, this is going to be a finish cut. We're going to run it at 100%. 4-flute end mill. Cutting speed again is 100. Our chip load should be 0.002. And our depth of cut should be 0.005. So let's see this. 80, 85, 90, 95 thousandths. Add this all together. We get 0.095 from an eighth of an inch. That should give us 30 thousandths left on the bottom of this part to finish this part up. This surface here that we end up with, this is going to end up being datum A. Okay, so now let's go to the mill. Okay, now carbide cuts mainly because it's hard, not necessarily because it's sharp. We're just going to take our part, which we've already sawed out. We want to make sure that there's no burrs on it whatsoever. And we're just going to sit it up on top of a couple of parallels. Now bear in mind that we have figured out already how deep each of these cuts should be. We'll take our part and just clamp it in the vise. Just clamp it in the vise. Now, we want to make sure that our quill is up inside the head just about as far as we can. We don't want it to be hanging out a whole lot because it creates a lot of vibration. Now, we said this first cut, we want to make it about 75 thousandths deep. And we're going to bring the cutter over on top of the workpiece. Drop the table down so we can bring it up to it. And what I'm going to do is I'm just going to bring the cutter down. We want to make sure the table's in the lock position up. We want to lock our cross slide on it. And I'm going to bring my cutter down until I just feel a touch. I want to lock that quill in place. Now, chips coming off from a carbide cutter, if they turn blue, that's perfectly fine. And we're we're going to run this at 600 RPM, 660 RPM. Slow this thing down. About 640 RPM. And we said it's going to take about roughly a second and a half to make each turn. So let's 1,000, 2,000, 1,000, 2,000. Oh, we need to bring the table up 75,000. So let's bring the table up 75,000. So it's at 50 now. So bring it around to 25. This is 75,000. So 1,000. It's just a roughing cut too, so we're not real worried about the surface finish. Okay. We left a little step on the back. Let's take that step off of there. Now, I want you to look at the surface finish of this and compare it to the surface gauge, the surface chart. Now, let's take the finish cut on this. Now, notice the surface finish on this, and watch what happens. I'm going to take a finishing cut, and I'm only going to bring it up, about 3/5 thousandths. We'll turn it on. We're going to change the speed to what it should be. Now, because we increased the speed, we're also going to decrease our feed rate because it's a finishing cut. Now, with finishing cuts, you start with the cutter off the part, and you're going to continue until the cutter comes completely off the other side of the part. The old timers, they like to throw the chips away from it. But the other side of this is, when we're face milling, if we have the cutter coming into the part, we eliminate that burr that the cutter would make. So you notice that there's more than one lay on this part. That's kind of a disadvantage. But if we get a nice flat surface with no steps in it, it's perfectly acceptable. I want you to notice the surface finish on this. Which surface finish looked better, the roughing cut or the finishing cut? Which do you prefer? I want you to think about that. Now let's move on to the fly cutter. Okay, so now we're ready to use the fly cutter. We're going to bring the fly cutter down. The fly cutter, we sharpen the bit just like you would sharpen a lathe tool. Now, the advantage to the fly cutter is we're going to be able to cut across the entire face of the part. So we only get one lay on the part. There's not going to be any lines on it. It's going to give us a real nice finish, but it's only for finishing cuts. We're going to bring the cutter down until we just touch the workpiece. Again, keeping as much quill in the machine as possible. Make sure that's locked. We'll make sure the table's locked. Now, we're only going to take about 10 thousandths off of this part. So we bring the table up a little bit. Our speed, it is high-speed steel, so it's going to be considerably slower than the carbide. And our feed rate is going to be considerably slower as well. And you can figure that out. I want you to figure that out. Slow this down. The flat cutter should start off the part and continue until you get to the other side of the part. So now I want you to look at this part, look at that surface finish, compare it to the surface gauge. Tell me which surface finish you like the best so far. Now let's move on to the end mill. Now you'll find this cutout on many of the end mills. When we put this in the collet, you want to make sure that we're going past that point, almost to the point that the flute, the edge of the flute, comes up with the edge of the collet before we install that. Now, we want to make sure that the cutter's running in the forward cutting direction. If this cutter touches the part spinning backwards, the second that it touches the workpiece, you've taken the edge off of this cutter and it doesn't cut as well as it should. This is also going to be a finishing cut. And we'll lower the table down so that we can put the cutter right on top of the workpiece. Again, we want the quill up as far as possible. We're going to bring the cutter over, bring it down till it just touches the workpiece, lock the quill, come off the workpiece, and we only want to take about 10 thousandths off because it is a finishing cut. And we're going to take 10 thousandths off. Now I think we're ready to go. We want to check our speed and our cutting feed. Now we're going to take another cut. We're going to overlap it by about 3/4 of the cutter. If you see chips coming off there and the chips are blue, your RPM is too fast, you need to slow it down. If the chips are coming off and it looks like powder, your feed rate is too slow, you need to increase your feed rate. Now we're done with this surface A. I want you to look at the surface here, the surface finish. Which surface finish did you like the best? We're going to deburr this part and we're going to inspect it. So let's take a file. We're just going to knock the corners off for now. Next week we're going to talk about squaring one side of this up, and it'll be important that we understand about the deburring process. So let's take this over to the surface plate to check it out. Okay, so here we have a fingernail gauge or a surface comparison chart. We have our surface that we just finished milling. We want to check this against the chart to make sure that our surface finish is what it's supposed to be. 125, 125. This is the finish that we're looking for. We want to make sure that this surface is flat because this is now datum A. This is the bottom of the part. Make sure that the part is clean. Make sure that the surface plate is clean. We're going to take the part and take the thinnest feeler gauge you can find, which in this case is 1.5 thousandths. Hold the part and see if that feeler gauge goes in anywhere underneath this part. Okay. So, in this case, this part is considerably flat. We have completed side A. We want to make sure that we mark this as datum A. And it's important that we keep that as datum A. Okay?